The last thing I need to define for the first part of Unit 2 is a biconditional statement. To do that, I'm actually going to have you look back at these statements that we created with the conditional statement, if it's snowing then it's cold. Okay, so what we talked about in our last lesson is that the conditional statement and the converse do not have to be logically equivalent. Okay, the conditional statement and its converse do not have the same truth value in this situation. They are not logically equivalent. But sometimes they are, and that's what a biconditional statement is. So a biconditional statement is when the conditional statement, so the original conditional statement, and its converse, are logically equivalent. And logically equivalent means that they have the same truth value. That's what logically equivalent means. So the statement we did in our last lesson was not biconditional, but we do have a lot of statements that are. One example here I've given you is a definition, because actually definitions are always biconditional. So let's look at our example here. If two segments are congruent, then they have the same measure. Okay, let's write the converse of it. So remember, if the conditional statement was if P then Q, our converse is if Q then P. It's when we switch the hypothesis and the conclusion. So our original hypothesis was this. I don't have the word then, but I'm going to circle my comma. Okay, so the converse is going to be if they have the same measure. And I don't really want to start the sentence with they. I'm going to say two segments. Okay, that's what the they are. So I'm going to go ahead and write this. The converse of this statement is if two segments have the same measure. If two segments have the same measure, then, and now I can say they instead of two segments. Okay, so then they are congruent. Okay. Now, these are both true statements, right? If two segments are congruent, they have the same measure. If two segments have the same measure, they're congruent. I mean, that's the definition of congruent. So what that means is we can actually go ahead and write this as a biconditional statement. Symbols that you might see associated to this are if and only if P, then Q. Okay, a double-ended arrow here, because it works both ways. It's biconditional. It goes both ways. So the way we write a biconditional statement, I'm going to go back to my original statement here, and what's going to happen is, remember, this isn't really part of the hypothesis. This was our hypothesis, and this was our conclusion right here. And what we're going to do is we're going to take out the words if and then. Of course, this sentence didn't even have a then. And what we're going to put with the biconditional is if and only if. And we're going to stick that right in the middle. So it's going to become two segments are congruent if and only if they have the same measure. So the first if comes out, the middle part comes out, and we put the if and only if right in here. So two segments are congruent. And now I'm going to do my biconditionals if and only if. If and only if they have the same measure. Okay, So just to recap, not all statements are biconditional. The example we did in our earlier lesson proved that, okay? A conditional statement and its converse do not have to be logically equivalent. When they are, which is in the case of all your definitions, you can go ahead and write it as a biconditional statement. You take out the first if, you take out the then, and in the middle you put your if and only if. Sometimes you see that abbreviated like this too. If and only if. So it became, let's see if I can get that down there, okay? Two segments are congruent if and only if they have the same measure.